Okay, welcome. This is the solution to the problem of the day, which was posted yesterday, 7:10. So part A, I said, given the del operator, which we've been using this, and a vector written in a summation notation like we always do, prove that the divergence of V, which is del dot V, is equal to this, the covariant derivative of this vector component, but it's the vector component J with respect to J. So this is new to us. Okay? So we got del, here's del dot V. Now what's the first thing we can do here? Well, we can pull these components outside of the dot product. So it'll look like that. Well, what's that? Okay, we know what that is by now. That's the metric tensor. So we've got these three components, the metric tensor. We also have the inverse metric tensor. We put these two together. What do we get? We just get the identity matrix. So that just leaves this. Okay? That was pretty straightforward. So that is the divergence of V, is this expression. Now, I said in part B, expand this covariant derivative, this one, and prove that the Christoffel symbol, which you get from that expansion, is equal to just this. And you notice this is a contracted Christoffel symbol, which we also have not done. Okay? So let's write it out the way we know how, which is you always take the partial derivative of whatever this is with respect to the coordinate, which is J, right? Then we write down our Christoffel, the symbol, and remember this is a contravariant component, so we get a plus sign, and the summation index goes low to high, which obviously just leaves these two contravariant and covariant indices, J, J, I. So this is a double sum, right? So let's break this guy out and expand it the way we know how, which is like this. It's the way we always do it, right? So we got 1/2 the inverse metric, the tensor, and we see we only have one contravariant component, J, so it has to go there. That becomes a summation index. Then you fill this in the way you always would. So you pick one of these covariant indexes, put the other one down here, pick the other one, put the other one down here. The negative sign always uses these two covariant indices together, like that, which leaves the summation index. Okay? Now let's look at these last two terms, the second and third term. Look at this. I just expanded this coefficient into them, right? So you see something here is that everything here is a summation index, J, J, M, M, J, J, M, M, except I. Well, what if we just change in this first term here, just change this J to an M and change this M to a J? Because they're dummy indices, we can do that. It's totally legal. Look what we get. Now, given the symmetry of the metric tensor, right? GMJ is the same thing as GJM, and this GIJ is the same thing as GJI. So these two things just cancel. That only leaves this part. So that was the proof. Now, where are we going with this? We're going to do one more video in between to actually calculate this expression up here in spherical the coordinates, so we see how it's done. Then after that, we're going to use this to develop a true tensor equation for the divergent that is much easier to use than this. That's where we're going. All right, see you later.